Good morning. Today we're going to learn a few things about the sweet potato, how it works, because if we don't know how it works, we can't begin to fix it. But first, how we got here. Really like to thank the support of the Louisiana Sweet Potato Commission because they provided us support and funding all these years, not to solve big problems, but hopefully to develop proof of concept, evidence or data to get support, get more funding, and hopefully solve the bigger problems. So first of all, I'd like to thank Lamb Weston for funding cutting-edge research that enables us to use gene expression data to predict the fertilizer requirements of sweet potatoes by variety. So it's funding a PhD student, Lisa Arce. I'm going to let her tell the story later. I'm not going to get in front of you all here and tell her story. We also get funding from Gerber Products Company to solve an emerging industry problem about the presence of toxic elements in sweet potato. And so our PhD student, Ms. Mayan Bravo, is also going to tell her story a bit later. And finally, we also have funding from the Israeli-U.S. National Agricultural Fund to investigate two things in sweet potato: how it responds to drought, so Don can better select for drought-resistant varieties, and secondly, to identify the signal that tells a root to become a storage root. So all these years we've been wondering what makes the root transform to a storage root, because if we know what it means, then maybe our desired outcome is more US ones per hill instead of none. And our graduate student, Ms. Marisa Barbosa, she was kind of said, I'm not going to talk to you. You're fine, Marisa. You're going to be fine. This is your story. You tell your story, okay? So very often we go to the field and look at what's going on with the crop. And sometimes it's yellowing. And sometimes we pull soil samples, pull tissue samples. And frequently it's a bit late to fix the problem. It's already happened. So what if we can hear what the plant says? What if we can communicate with the plant? And that's where gene expression profiling comes in. Think of the plant DNA as a complete cookbook of all the recipes it needs to establish and root, survive, thrive, and be productive. Now, at any given moment in time, it's only expressing certain genes. It's only cooking up, a steak for dinner or not dessert. Certain times, for example, if it's in a drought condition, it's only expressing genes that enable it to mitigate drought conditions. If it's subjected to nitrogen deficiency, it's only expressing genes that enables it to adapt to nitrogen deficiency. So what if we can read this cookbook in real time? That's where work comes in. So really, we're using cutting-edge technology, but believe it or not, this is where we started here. So I'm just going to tell this story. So we started 8 years ago trying to understand the problem, and believe it or not, this is a PCR machine. It's got 8 wells. We started with this. It's about, it's a disposable PCR machine, but it enables us to really provide proof of concept that yes, it is possible to isolate a phosphorus gene that might enable us to predict the phosphorus requirements of a sweet potato. I'm not gonna upstage Lisa, that's her story, but this to get to tell you that how we got here was a series of trial and errors and providing proof of concept, and we did greenhouse work and field work to make sure that our genetic expression, which is half the story, is telling us the actual story. So what does it mean for sweet potato production? Number one, it means that we can customize the amount of phosphorus or nitrogen that a particular variety will require. That's a game changer. Second, with our advanced tools, we are able to identify markers that enable a variety to have less lead uptake or understand how a variety adapts to heavy metal stress. That's very important because, again, we can use this knowledge to manage our crop better so that those providing for Gerber and other baby food manufacturers can better manage their crop. And thirdly, understanding the signal that tells a root to become storage roots, again, is a game changer. That means if that signal is something we can manage, then again, that means a whole lot because number one, we can customize the application of fertilizers. We only need to apply what's needed at the right time. And finally, reduce the cost of production. Fertilizer is getting very expensive, and now what we used to put out in liberal amounts, we're now getting very careful. So being able to understand what the plant communicates is important, and we're using this as a tool to improve our management of sweet potatoes. Now it's time for our graduate students to talk about their stories. So first up, Lisa RSA, she's been with us for how long, Lisa?
3 years.
3 years. So they're up here during summer conducting greenhouse and lab work, field work especially. They organized this trial, they planted this, I just helped. So I'm letting them talk. And now they're going to tell their stories. Go ahead, Lisa.
Again, good morning, everyone. I'm Lisa Arce. I'm working with Dr. Don Labonte and Dr. Arthur Villardon. So the fertilizer recommendation in sweet potato production is 45, 80, and 120 pounds per acre. Well, at least here in Louisiana. However, the big question here is it best or is it good for all of the cultivars that we are growing? Because based on our research or our studies that we have conducted, it's not best all the time. And certainly more is not always better. So that's why we wanted to investigate what's the molecular basis behind cultivar-specific fertilizer requirement. So we used molecular techniques, we dig deeper and we used molecular techniques to investigate that. And from our digging, we came across the world of transporters, the nutrient transporters. So think of them as delivery trucks. They transport the nutrients from the soil to the roots, from the roots throughout the plants. And what we found in our initial investigation is that the more active the transporters are, the less it requires nutrient. But if they are lazy, it performs better if you add more of that nutrient. So we have validated this in the greenhouse trials for 2 years now. And on the 3rd year, we decided to do it in the field trial. So that's why we have it here. And we have some samples here for 60-day-old plants. And I just want to share to you some of the contrasting phenotypes that we've observed, which validated our molecular studies. So let's start first with nitrogen. Can you raise, Mommy? And then I'm gonna have Beauregard over here. Yeah. So on my right, on our right, that would be less, and that would be more nitrogen. So you can observe there that the Orleans with less and more have quite a comparable yield. However, for Beauregard, more is better. And when we check the transporter activity, it occurs that this one has lazy nitrate transporters and that one has active ones. And that is also same thing with phosphorus. So, okay, so this is Biobel and double, and then the other one is Evangeline. Okay, this is less and this is more. Okay, so you can see there that for Biobel, there is almost quite similar outcome between no phosphorus and with the double rate of phosphorus. But for Evangeline, you can definitely see here, if you remove phosphorus, it's wonky. Also, this phosphorus trial also confirmed what Dr. Arthur observed for Biobel, wherein in 2014, if we grow Biobel under low phosphorus condition, it will form storage roots that are more blockier shaped. See over here compared to a more tapered ones. And this is important because processors like blockier shaped roots for more efficient and uniform slicing. Now what's interesting is that, again, this validates our activity of our transporter, but in this case, phosphorus transporters. Now for potassium, although I haven't started yet the potassium molecular works, but our field trial would definitely show the cultivar difference. This is surprising because asang baliha, that one. So this is Biobel, this is Evangeline. Can you show the less? Less, more. So it seems Evangeline wants more potassium, but Biobel likes, Evangeline likes less potassium, but Biobel likes more potassium. So what is it for us? Our results would be for all of you. Well, if we are able to synthesize or combine all of this data from our molecular works, from our greenhouse trials, from our field trials, Again, Dr. Arthur just mentioned, we will be able to tailor cultivar-specific fertilizer requirements. That means no more spending money for those fertilizers or nutrients that your specific cultivars doesn't really need. I know we still need to do a lot of validation in the greenhouse, in the field, maybe a couple of years in the field trials. But one thing is for sure, we are one step closer to achieving our main goal, which is to help our growers earn more by spending less.
Okay, good morning once again. So while my colleague Lisa and Marissa will talk about nutrients and their role in improving the yield of our sweet potato and our production, my work is to focus on how to keep our growers produce healthy and safe sweet potato. So a year ago, the Food and Drug Administration released their Closer to Zero action plan. This includes the enforcement of proposed action levels and the adoption of best management practices to reduce heavy metals such as lead, arsenic, and cadmium in the soil in our raw product or our storage roots, for example, sweet potato. Now, Gerber, as one of the producer of raw product or sweet potato baby food, is very much affected by this. And by that, they want to collaborate with LSU AgCenter, and with that, Dr. Labonte and Dr. Villardon develop a proposal to solve or to mitigate this problem. So I am Mayan Arces Bravo, a PhD student from Louisiana State University, and our work is trying to bridge the knowledge gaps in what we know about heavy metals and their effect on sweet potato, and also to make sure that our favorite vegetable continues to be healthy and safe to eat for everybody, especially infants and children. So I don't have a setup here, but I have done my work in the greenhouse and on the area that have elevated levels of heavy metals such as arsenic, cadmium, and lead. One way to reduce heavy metal in the soil and to reduce the concentration in our storage root is to use soil amendments. The role of the soil amendments is to hold the different heavy metals in the soil and to avoid this heavy metal to be taken up by our sweet potato. Now, soil amendments such as agricultural lime, we know agricultural lime, gypsum, wollastonite, and biochar are used in our experiment. So the principle behind, they locked up this heavy metal in the soil and they are not taken up by our sweet potato. Now, one highlight of our experiment is that application of these different soil amendments will help lower the concentration of these different heavy metals in the soil, thus further result to lower concentration of heavy metal in our storage roots. So we would like that. So the action plan that was released by the Food and Drug Administration is 20 parts per billion. So we don't know what's in the soil, but we can do that by analyzing the soil and application of the different soil amendments. Now, another highlight of our experiment is the difference between the accumulation of heavy metals between different cultivars. For example, we have Bourgard and Biobel. We have found out that in the same concentration of heavy metal in the soil, Bourgard Biobel has lower concentration in the storage root compared to our Bourgard. Now, we would like to say, what's going on? They are the same sweet potato, but the mechanism behind is that Biobel produces larger and more storage roots, and Bourgard, as you can see, lesser. So the mechanism behind is the dilution effect. The concentration in the same area taken up by the plants is the same, but with more sweet potato storage roots, the concentration of heavy metal is diluted across more tissues, resulting to a more lower concentration of heavy metal per gram of sweet potato. So this is what we call as dilution technique. More root biomass, lesser concentration in the storage roots. Another highlight of our experiment is that what are the mechanism or what are the genes that are responsible for this? We are still doing greenhouse work and we're trying to do molecular work in order for us to answer what are the differences between Biobel and Bourgard. We're still doing that, we still cannot confirm, but we're looking at different genes that mitigates the transport from the soil to the storage roots of these different cultivars. But for now, we can say that the combination of soil amendments and the use of cultivar that has lower concentration or low accumulating capacity of our heavy metal can answer or achieve closer to zero action plan, and also can help us produce healthier and safer sweet potato storage roots in the generation to come.
So good morning, everyone. Once again, I am Marisa Barbosa. I'm glad to meet you all today. One of the highlights of my PhD research is to identify the critical signal that turns on the process of storage root formation. So we all know that sweet potato adventitious roots or a single sweet potato cutting can produce anywhere between 4 to 10 adventitious roots. However, not all of these roots will develop into storage roots. Some of these remain thin, others become lignified and thicken, but they don't swell. And so the important question there is, what is the trigger that transitions or that transitions the formation of storage root formation. And we have found that phosphorus and nitrogen are critical signal for storage root formation. The importance of these nutrients could vary between cultivars, as what Lisa discussed earlier, that different varieties, they respond differently to different fertilizer requirement. And so we also highlight that the rate and timing of phosphorus and nitrogen application are crucial for storage root development. This is because once these nutrient levels drops below a critical threshold, it will signal the root system to increase the flow of sucrose from the source tissues, and that induces storage root formation. So that means that phosphorus and nitrogen has to decline over time, and once a specific reduction threshold is reached, it will signal the root system to initiate storage root formation. So for example, this one was applied with higher P, about 160 pounds per acre, and this one was applied with 80 pounds per acre. So, and you could tell like which one is desirable and which one is not. So in this case, if we apply higher amount of P, it could delay the signal, it could delay the induction of storage root formation, and that results to inconsistent storage root development. That is because higher P rate could leads to, or it will take longer time for it to decline over time and reach the specific threshold to initiate storage root development. However, if we also apply zero amount of phosphorus, it will also significantly affect storage root yield. It will lead to poor results. So that means that the presence and timing of both nitrogen application are critical for storage root yield. So how does this work? What is important is to identify first each cultivar's specific phosphorus and nitrogen requirement, because my research shows that we really have to optimize it, or we really have to pinpoint the threshold. And again, it has to decline over time. So in the evidence I gathered, it kicks in at 50% reduction in phosphorus, at least for Beauregard sweet potato cultivar. For other varieties, this could differ. That's why that cultivar-specific nutrient requirement is critical. Work emphasized that we really need to manage the amount and timing of both phosphorus and nitrogen application, probably based on variety, in order to achieve consistent storage root yield.
But the goal is to classify varieties into low and high initially, and maybe a medium there. Yes, so, but what part of a long-term goal? So I'm gonna end up today addressing a question during planting. Leaf on or leaf off on the slips? So what we have here, if you can come closer, are leaves that we essentially put in sand. This was planted, I believe, June 12 or something. So this has been in the pot for about 40 days now. Question, will it form storage roots? We have an ongoing bet with the students. I say, it forms. I say, it's not. Why? We have the leaf. The leaf is your solar panel. It creates energy. It creates sugar. You have a vascular tissue from the leaf to the base of the stem or the root. And that's all you need to form storage roots. But the question is, will this leaf form storage roots? Because if it will form storage roots, then that tells you that you know a bit more about how this thing works. Because if you can control storage formation, if you take something out, it doesn't form storage. It's a way to test our hypothesis. So one more call. Is it storage roots or none? Anybody?
Wait, is that leaf on or off?
Well, the idea is when we plant slips. All right, so Yeah, so very frequently when we plant the slips, many of our workers or crews take the leaves off because it's easier to manage on the planter, right? Now, does it benefit the planter or, or the plant? That's the question. Why are we taking this leaf? What will happen if we take this leaf off like that? And very frequently it goes to the ground and stays, it will root, right? But something else happens if you take the leaf off. So if we can show that this leaf contributes something to storage root formation, that means that maybe we need to leave the leaf on and not take it off. So,
but you have leaves on both of those stems.
Yes.
Okay.
Which one? Yeah, which one was which? Did they
Oh.
both planted like in the treatment?
Yes.
Both of them planted.
We took the leaf like this, stuck it in the sand.
They were both planted leaf on in that.
Yes. No, this is just single leaves.
Oh.
Just single leaves.
Okay. So for both of those, there's no.
Yes, just
Right, but isn't the hypothesis to get rid of the leaf completely and have a bare stem?
what it will tell you that if this forms storage roots, then we are benefiting from whatever the leaves doing at planting for it to establish faster and root faster. So again, this is not a stem, it's a leaf that we stuck in the sand.
I
No?
always heard in cuttings that like the leaves are basically like they're just an outlet for water. Like, they dry out.
All right, okay, so we have two here, BioBell and Borgard. So I'm gonna do BioBell first, so check. And there is your little storage roots pass it around. Marisa, that's one, right? Okay. And that's your Borgard. Pass it around. So
All those nodes and tissues, even if it's off a leaf, are almost kind of totipotent.
you need the leaves to be able to manufacture more sugars. Yes. Yeah. But that's all that we have. So again, the message is the more we understand how the plant works, the more we're able to solve the problems and know what's the base for the problem. So thank you all for your attention. And if you have any questions, the students will answer them. We often talk about the 4 R's of nutrient management: the right source, the right rate, the right time, and the right place. Our research shows that there's a potentially 5th R, and that is the right variety. Typically, when we manage our nutrient applications, we only use soil testing and yield goals. But our research shows that knowledge of the variety is very important. Just like some trucks have better mileage than others, some sweet potato varieties are better at it in obtaining phosphorus in the soil. This can mean a difference between wasted fertilizer and optimized yield. Our research classifies sweet potato varieties as P-efficient varieties and P-responsive varieties. The phosphorus-efficient varieties have very elaborate root systems that can find the phosphorus in the soil. They also have phosphorus-responsive genes that tell the plant that phosphorus is low and able to utilize available phosphorus reserves in the shoot. The phosphorus-responsive varieties are high-octane performers. They need higher phosphorus to achieve their yield goals. So how does a grower use these results? There's 2 scenarios. In the first scenario, a grower might have a low phosphorus testing soil. He can opt to use a phosphorus-efficient variety, and this acts as a safety net where the high-performing varieties might fail. The second scenario involves a high phosphorus testing soil where a grower can provide the inputs necessary to sustain the productivity of high phosphorus responsive variety. The long-term goal of this research is to ensure that the grower will produce more with less.